Stars are classified by color. Color can be measured independently of the apparent brightness of the star. Stars are approximate blackbodies, and thus their colors are due primarily to their surface temperatures. 3 methods of measuring a star's temperature will be discussed. The Harvard classification scheme is the result of work done in part by the American astronomer Annie Jump Cannon. Stellar colors and surface temperatures are specified by letters that are now scrambled due to those letters having been used in a previous classification scheme. Some star catalogs had already used early schemes, and so it was decided not to reorder the letters. Going from blue to red, or from high temperature to low temperature, the classification is O, B, A, F, G, K and M. One mnemonic to remember the order is, oh boy, a failing grade kills me. Temperatures go from tens of thousands of Kelvin to a few thousand Kelvin. This classification is further refined by specifying additional numbers, from 0 to 9, such as G0, G1, G2, etc. For a given classification letter, the higher the number, the cooler the temperature. This may take some getting used to. The Sun is a G2 star. A G7 star would have a cooler surface temperature than the Sun. This slide shows trends in an increasing direction using the arrows. For example, as one goes from M to O, the surface temperatures, radii, masses and luminosities increase. However, the lifespans and relative abundances decrease going from M to O, that is, they increase going from O to M. Shown here are the color labels and numbers representing the temperatures, diameters and masses for the different stellar classifications. Recall from Chapter 5 and the discussion of blackbody curves and Wien's law that, since stars are approximate blackbodies, we can calculate the surface temperature of the star by using the wavelength at which the curve peaks. The shorter the wavelength where the peak occurs, the higher the surface temperature. One difficulty with this method is that the spectra are full of absorption lines which can obscure the peak, like the spectrum shown at the bottom left. Another possible difficulty is that the curve may peak outside the visible spectrum or outside the wavelength range of the measuring instrument used, like the spectrum shown at the bottom right. Using this method is the least precise of the methods that will be discussed. A more precise way is to simply sample the spectrum at 2 or 3 different wavelengths. To do this, light is passed through a filter that lets in only a very narrow band of light that is centered on a particular wavelength. 2 such filters are a blue filter, letting in a narrow band of light centered on 3,500 angstroms, and a visual filter centered on 5,300 angstroms. The apparent magnitudes through each filter are then calculated, and then the magnitude through the visual filter, V, is subtracted from the magnitude through the blue filter, B, resulting in a BV index or color index. At different temperatures, a unique color index results. Sampling light in this way, one avoids problems associated with using Wien's law. This method is a more precise way to measure temperature. Shown here is the relationship between the temperature in Kelvin and the color index. If you study this graph, you can see that, for high-temperature stars, slight uncertainties in the color index results in large uncertainties in the temperature, whereas slight uncertainties in the color index for cooler stars don't cause such large uncertainties in temperature. Thus, this method tends to be more precise for stars with temperatures less than 10,000 Kelvin. The most precise of the 3 methods to measure temperature is to examine the absorption lines themselves. The particular elements create absorption lines, and between what energy levels those absorptions occur is very temperature sensitive. Looking at the graph below, hydrogen absorption lines tend to be the strongest for A stars and tend to be rather weak for G stars, like our Sun. Helium lines only tend to occur for the hottest stars and lines by molecules in the coolest stars. Shown here are spectra of different stellar classes. The hottest stars tend to show fewer and weaker absorption lines. Cooler stars show many absorption lines. Some lines are very strong. Shown here is a comparison of the spectra of a B0 star and a B6 star. Both show hydrogen absorption lines, but the B6 star, a cooler star, shows stronger absorption.